Hello guys, welcome to the next part of the video where we were solving the following integration. So this was basically the integration that had to be done, and our proceedings so far, I'll summarize it as follows. So this was our proceedings from the last video. We had defined a function f of a, and we had parameterized the function sin x by x, the integral, as follows, right? We noted sin x by x dx equals to I. So these were the two results that we also had noted. Now the last step that we also did was as follows. So it was minus 0 to infinity e to the power minus ax sine of x dx. So this was basically the derivative for the function f dash t. Now we are required to find this integral. So let p equals to integral of e to the power minus ax sine x dx, and we are trying to find the indefinite version first. Okay, so we remember the Eilert rule for doing a product of an exponential function and a trigonometric function, and we remember that in the Eilert rule the trigonometric came first and the exponential came second. So this is the first function and this is the second function. Then IBP we have, so first function, this sin x integral of e to the power minus ax dx minus, so first function should be differentiated as cos of x, because the derivative of sin x is cos x, and integral of e to the power minus ax dx, and then we again have a dx. Now we know that the integral of e to the power minus ax dx for a constant a, which is independent of x of course, is given by my minus 1 by a e to the power minus ax, right? So this becomes minus e to the power minus ax sin x by a, and this becomes minus cos x e to the power minus ax by a dx, but there is an extra minus which comes, which makes this thing as a plus, right? Okay, now in this part we can repeat the same thing, where we can take this function as the second function and this one as the first function, and this shall give us so integrating cos x into e to the power minus ax would give us cosine of x into integral of e to the power minus ax dx minus differentiation of cosine x is just minus sin x, so this is plus sin x, and what we will have here is basically integral of e to the power minus ax dx, another dx, right? So this would be the expression basically. Now this part was minus 1 by a to the power minus ax sin x. This part was 1 by a cosine of x into e to the power minus ax, which is basically e to the power minus ax upon a, and there would be a minus sign here. And for this part we can do as follows. So this minus 1 can basically be written in front, so I'll just write it in front, just that we don't mess it up in the writing section. So and for the sin x part we have another minus, I think, because the minus will contribute from this part. Minus 1 by a integral of e to the power minus ax sin x dx. So when we expand everything, what we get is as follows: p equals to minus 1 by a e to the power minus ax sin x plus 1 by a squared cos x into e to the power minus ax. Actually it's minus because we had forgotten the minus sign, and then there was another minus, which is minus 1 by a square integral of e to the power minus ax sin x dx, right? But if you remember, this part is just p, so what we do get is as follows: p equals to minus 1 by a squared common a e to the power minus ax sin x plus e to the power minus ax cos x, and there is a minus p by a square. So taking p common on the left hand side, we get p plus p by a square equals to minus e to the power minus ax by a squared whole into a sin x plus cos x, right? This gives me p whole into 1 plus 1 by a square equals to minus e to the power minus ax whole into a sin x plus cos x by a square. And simplifying this, we get p into 1 plus a square by a square equals to minus e to the power minus ax by a square into a sin x plus cos x. The a squares cancel off, and we get p equals to minus e to the power minus ax by 1 plus a square whole into a sin x plus cos x, right? So this is our desired integral, and we can go back and see what p was. P was basically the positive portion actually, so it was the indefinite integral. So then therefore 0 to infinity e to the power minus ax sin x dx would just be equal to this portion e to the power minus ax by 1 plus a square into a sin x plus cos x, and it would be rather from infinity to 0 because of the negative sign, and the answer would be something around. So when you put 0 in here, what you get is 1 by 1 plus a square, and when you put infinity you get a 0. So this is basically the answer, right? This is basically the answer, and therefore f dash a should be equal to minus 1 by a square plus 1, right? Now we can integrate it back to the following form, where we have integration from 0 to infinity f dash a dA equals to minus 0 to infinity dA by 1 plus a square. Now by fundamental theorem of integral calculus, we have f of infinity minus f of 0 equals to minus, and this is just the antiderivative of the antiderivative is given by tan inverse a or arc tan a, because I will just write it here, ddx of tan inverse x, which he had actually proved before, is 1 by 1 plus x square, right? So 1 by 1 plus a square will have an antiderivative which is tan inverse of a. So this would give you tan inverse of a from 0 to infinity, which would basically mean that tan inverse infinity minus tan inverse 0. Tan inverse infinity is pi by 2 and tan inverse 0 is 0, so it will give you minus pi by 2. And on the left hand side, we know from our previous findings that f of infinity is 0 and f of 0 is basically I. Therefore 0 minus I will be minus pi by 2, or therefore I would be pi by 2, which is our answer, because I was our desired integral. So as you can see, this problem basically tried to punch in all the necessary stuff required to solve a problem of this magnitude, and this, believe me, this is even just the start, because in literature of mathematics or integration, there are so many interesting integrals that mathematicians are yet to solve, and this one was solved somewhat like 200 to 300 years ago. And what you see here is a technique that was mostly used by Feynman. So Richard Feynman, who is a renowned was a renowned physicist basically, and a very proficient mathematician as well. But this kind of methods have been used over centuries, and these methods, you need to apply them to your own problems to make sure that you have another way, another angle to look at your problems. So as you can see, integrals are very fun because it's just not like differentiation where you know what to do already. So you literally have one rule to find the derivative, which is the chain rule. There is nothing else, right? So that's how it works. Anyway, so I hope you liked the video, and please do check the link in the description for the Breatter Maths app, where you can have all the theory and all the notes regarding to whatever I'm teaching here. Thank you very much and have a good day.